Hello. In this video, we'll be reintroduced to the concept of mathematical induction. So remember that the set of natural numbers is described as n containing 1, 2, 3, and so on. And we shall endow this set with the natural addition and multiplication operation. So we endow n with the usual addition and multiplication operations. To proceed, we will need to make the following assumption, and because this assumption is something that we can't prove, we call it an axiom. So our first axiom is called the well ordering property of the naturals. And this property says the following: every non-empty subset of the naturals has a least element, has a smallest element. This is the well ordering principle. So in other words, if we let S be a non-empty subsets of the naturals n, then there exists M, which is an element of S, such that M is less or equal to S for all little s in our set S. And this axiom leads us to the following result. And this result is the principle of mathematical induction. Theorem: the principle of mathematical induction. So let me state this principle for you. The principle of mathematical induction says the following: let S be a subset of the naturals such that 1, the number 1 is an element of S. Secondly, for every k in the naturals, if k is in S, then k plus 1 is also in S. Then this given set must be the set of all natural numbers. So in other words, these two conditions, condition 1 and condition 2, essentially completely characterize the set of all natural numbers. To prove, if you give me a subset of the natural numbers, if I want to show that this set is the set of all natural number itself, then I need to essentially prove two things. First, I'll prove that the first element of the natural numbers is there, so 1 is an element of the set. And second, I'll prove the following conditional statement. For every element in the set, the next element, the element which is obtained by adding 1 to the given elements, is also in the set. So if 1 is in there, then appealing to 2, property 2, 2 is in there. Appealing again to property 2, 3 is in there. Again, 3 is in there, 4, and so on. And you sort of iterate this process indefinitely, and then you recover the entire set of natural number. That is the principle of mathematical induction. So let's prove the principle of mathematical induction. Suppose that there is a set S which is contained in the naturals satisfying property 1 and property 2, but somehow S is not in the natural, is not equal to the naturals. Next, the complement of S in the naturals given by n take away S is the collection of all x in the naturals such that x is not in S, of course. This set is not empty, right? Because S is not the whole thing. Now, by the well-ordering principle, the set X, which is the complement of S in the naturals, has a smallest element which we denote by M. Now, since 1 is an element of S, then clearly M must be bigger than 1. Now M minus 1 is less than M, and since M is the least element in is the least element in X, it follows that M minus 1 cannot be in X, so M minus 1 must be in the set S. Now, since property 2 holds, then M minus 1 plus 1 is in S, thus little m is in S, and at the same time little m is not in S, and we have reached a contradiction. So we can then conclude it is now safe to say that the claim holds, which means that S must be equal to the set of all natural numbers if property 1 and 2 holds. Okay, so let us consider a sequence of mathematical statement P of 1, P of 2, P of 3, P of n, P of n plus 1, and so on, parameterized by the naturals. Now, to prove that for every k, which is a natural number, P of k is true, it is sufficient to prove that the set S, which contains all k's which are natural numbers such that P of k is true, it suffices to prove that this set is equal to the natural. And so to this end, we may appeal to the principle of mathematical induction, and we'll show, to this end, we'll show the two things. We just need to show that P of 1 holds, right? And this is called the basis of induction. And in the second step, we need to show that we need to show the following implication: if pk holds, then pk plus 1, the k plus 1 statements, will hold as well. And this is actually the meat of the proof of induction, of the mathematical principle of induction. This is known as the inductive step. So a proof by the principle of mathematical induction has two main steps. The first step is to prove that, so you have a sequence of statements, P1, P2, and so on. You first show that the first statement is true. That's the basis of induction. And secondly, you show the following implication: if the k statement holds, then the k plus 1 statement must also hold. And that part of your proof is called the inductive step. We'll come back to this later. There is a second version of the principle of mathematical induction. So let's call this here principle of mathematical induction, part 2. And according to this principle of mathematical induction, this allows us to start our basis of induction with a statement P and not, where your starting point n naught doesn't have to be 1, it just have to be at least 1. And the format is very similar. So to prove, so here to prove that Pn is true for all natural number n bigger than n naught, it suffices to show two things. One, P sub n naught is true. So this becomes the first, your basis of induction, the first statement that you have to prove. And then after that, you will prove that for all natural numbers k bigger or equal to n naught, pk holds implies that p of k plus 1 holds as well. Okay, all right, so enough with the formality. Let's dive into some specific examples. All right, so example, let us prove that for every natural number n, 1 square plus 2 square plus plus n squared is equal to n times 2n plus 1 times n plus 1 over 6. Whenever you see a statement, an expression or an equation involving a parameter n, which is a natural number, something holds for every natural number, you should be thinking about proof by induction. All right, so let's prove this by induction. So remember that a proof by induction has two parts. There is a basis of induction, and then there is an inductive step. All right, so for the basis of induction, we verify that for n is equal to 1, 1 times 2 plus 1 times 1 plus 1 over 6 is equal to 6 over 6, which is clearly 1, which is 1 square. Thus, the basis of induction holds. Now, for the inductive step, we need to prove the following implication. If 1 square plus 2 square plus plus k square is equal to k times 2k plus 1 times k plus 1 over 6, then 1 square plus 2 square plus plus k square plus k plus 1 square is equal to k plus 1 times 2 times k plus 1 plus 1 times k plus 1 over 6. And so the inductive step, okay? So the inductive step is a direct proof, involves a direct proof, right? Where you have these statements here, whatever I'm highlighting in green, is the inductive hypothesis. And the second statement, which is in yellow, is what I call the inductive conclusion. Right, so we want to establish this direct implication, and we have at our disposal this implication, and we have at our disposal a variety of technique, and one of them is a direct proof technique. So let's proceed directly. So to establish this, let us assume that our inductive hypothesis holds. So that means that 1 square plus 2 square all the way till k square is equal to k times 2k plus 1 times k plus 1 over 6 for some natural number k where k is greater or equal to 1. All right, then let's look at the inductive conclusion. Then you want to show that inequality holds. So let me start with the left hand of my equality. Then 1 square plus 2 square plus dot 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 plus k square plus k plus 1 square is going to be equal to, we know that the first k term by the inductive hypothesis are k times 2k plus 1 times k plus 1 over 6 plus k plus 1 square, and this is by the inductive hypothesis. Now we will put this in common. We'll write this with as one big fraction. So common denominator gets k 2k plus 1 times k plus 1 plus 6 times k plus 1 square over 6. And I suppose we can factor a copy of k plus 1 out. Factoring that out, we get k times 2k plus 1 plus 6 times k plus 1 over 6. And then we can expand things out. So we get k plus 1 times 2k squared plus k plus 6k plus 6 over 6. And that will be equal to k plus 1 times 2k squared plus 7k plus 6 over 6. And remember that what we want to show that we get this expression here on the right hand side. So we already see a 6 here, we see a k plus 1 there. We just need to work on this polynomial 2k squared plus 7k plus 6. We need to work on that a little bit. So maybe let's try to factor this. So we'll try to factor this by grouping. 2 times 6 is 12. So we look for you look for two numbers such that two factors of 12 adding up to 7. So 3 and 4, right? So we get k plus 1, 2k squared plus 3k plus 4k plus 6 over 6. And we'll factor by grouping. So we get k plus 1 times k. Here you get 2k plus 3. And then you factor 2 out of this group here. And 2 times k plus 3 over 6. Right? And now we can factor, so we have k plus 1 times 2k plus 3 times k plus 2 over 6, which is k plus 1 times 2k plus 1 plus 1 times k plus 1 plus 1 over 6, which is exactly what we desired. So then in the end we can then say that by the principle of mathematical induction, we now have that we can now say that 1 square plus 2 square plus dot 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 plus k squared is equal to k times 2k plus 1 times k plus 1 over 6 for every natural number k. And this is the end of our proof. Our next exercise involves the following. We want to prove that 1 cube plus 2 cube plus dot 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 plus n cube is equal to 1 over 4 n square times n plus 1 square for every natural number n. Okay, again, because this is a statement about something holding for every natural number n, we should be able to prove this by using a proof by induction. So, and then again, there are two steps. We need to check the inductive step, and then it will prove the. We need to check the basis of induction, then we'll prove the inductive step as well. So, the basis of induction holds since for a natural number n which is equal to 1, if you plug n is equal to 1 on the right hand side, we get 1 over 4, 1 square, 2 square, which is 4 over 4, that's 1, which is clearly 1 cube. Okay, and often, very often, the basis of induction is pretty straightforward, and really the meat of the proof, the substance, is the inductive step. So now for the inductive step, let us assume that 1 cube plus 2 cube plus dot 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 plus n cube plus k cube is equal to 1 over 4 k squared times k plus 1 square for some integer k, for some natural number k, such that k is greater or equal to 1. Then looking at our inductive conclusion, remember we are aiming to connect. Our aim is to connect our inductive hypothesis to our inductive conclusion. So let's look at the inductive conclusion. At least the left hand side of the inductive conclusion will be 1 cube plus 2 cube plus dot 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 plus k cube plus k plus 1 cube. Now, if you look at the first k adent, this is precisely 1 over 4 k squared times k plus 1 square, and this is by the inductive hypothesis. Now, I'll need to put, k plus 1 cube there. Almost forgot that. All right, then now I will factor k plus 1 square out, and then we have here 1 over 4 k squared plus 1 copy of k plus 1. And I suppose we can write everything with the common denominator next. So we get k squared plus 4k plus 4 over 4, which is k plus 1 square. And factoring this out, we get k plus 1 square over 4. And that's 1 over 4 k plus 1 square. 2, I'm sorry, there's a 2 here, time k plus 1 square. So this is in fact this statement here, this is what we want to establish for the inductive step. This is our inductive conclusion that we have just derived. All right, so therefore, according to the principle of mathematical induction, we can now say that 1 cube plus 2 cube plus dot 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 plus n cube is equal to 1 over 4 n square times n plus 1 square for every natural number. For this example, we aim to prove the following. We want to prove that 5 power 2n minus 1 is divisible by 8 for every natural number n. So for the inductive step, we verify that for little n is equal to 1, 5 to power n minus 1 becomes 5 square minus 1, which is 25 minus 1, I suppose, which is 24, which is clearly a multiple of 8. Next, let us, for the inductive, this is for the basis step, for the basis of induction. I'm sorry. Okay. Next, let us suppose that 5 times 2k minus 1 is divisible by 8 for some natural number k. Then okay, so then that means that 5 to k minus 1 is equal to 8l, where l is some natural number or some integer. Okay, next, if we look at the inductive conclusion by replacing k with k plus 1, then we get 5 to k plus 1 minus 1 is equal to 5 2k plus 2 minus 1, which we can then write as 5 square times 5 2k minus 1. But now by the inductive hypothesis, uh, 5 to k minus 1, actually 5 to k is equal to 8l plus 1, and consequently 5 2k plus 1 minus 1 becomes then 5 squared. Let me replace the 5 2k by 8l plus 1 minus 1, which is going to then be 5 squared times 8l plus 5 squared minus 1, which is 5 squared times 8l plus 25 minus 1, which is 5 squared 8l plus 24. Okay. All right. So then, again, we can then rewrite this as 5 squared times l times 8, and we can write 24 as 3 times 8, and then we can factor this 8 out, so we get 8 times 5 squared l plus 3, or in other words 8 times 25l plus 3, which is a multiple of 8. So then this is in fact the inductive conclusion. So we have proved that if the inductive hypothesis holds, then the inductive conclusion holds, and then we can now derive that thus by the principle of mathematical induction, we can then say that 5 2n minus 1 is divisible by 8 for every natural number n. And this is the end of this proof by induction. Okay, so here we would like to prove that 2n is bigger than n squared for every natural number where n is greater or equal to 5. And this is an example where, again, our basis step doesn't start at 1, but instead start at 5. And also, you know, when mathematicians are working on a proof, they often go through a bunch of scrap work, various versions of scrap work, and they keep refining their work until they get to a point where they're satisfied. So let me show you a little bit some of the steps that are needed here, that how I think about problems, how I approach my proofs. So I know that here for the basis of induction, there should be no problem, because all I have to verify is that 2 power 5 is bigger than 5 squared, which is clearly true. So really the meat of the substance here, the work here is really the inductive step. And for the inductive step, here is my scrap work. Okay, so scrap. This is the part that I don't see, right? So I want to show here that 2 power k is greater than k squared will imply that 2 power k plus 1 is going to be bigger than k plus 1 square, right? And so if we assume that 2 power k is bigger than k squared, then 2 power k plus 1 will be 2 times 2 power k. And clearly by the inductive step, this will be bigger than 2k squared. And now we need to show, right, that 2k squared is bigger than k plus 1 squared. And that seems to be a little hard to do directly. So let me replace this by something which is maybe easier to approach. So this is really equivalent to 2k squared minus k plus 1 squared is positive, in other words. And if I expand this out, you get 2k squared minus k squared minus 2k minus 1 is bigger than 0, and this is equivalent to proving that k squared minus 2k minus 1 is bigger than 0. This almost looks like a perfect square. So to really turn this into a perfect square, I really need to add 1 here, and then I'll subtract 1 also. But I still have the negative 1 there. Right, so this is equivalent to this statement, which is then this is k minus 1 square, right, minus 2, which is positive. So this statement is logically equivalent to that statement. They are equivalent to each other. Right? So I can replace this statement by that statement. So to prove something like this, which is more complicated, it is enough for me to think about to prove this. Now notice that because k is greater or equal to 5, we can assume that then k minus 1 would be greater or equal to 4, and this will then imply that k minus 1 square is greater or equal to 16, and then by subtracting 2 we'll get that k minus 1 square minus 2 is bigger than 14, which is clearly a positive number. All right, so this shows you a little bit how I unpack the problem on a scrap work, but this is very informal. This is not something that I share with people. This is my internal thought to help me clarify my thoughts. Now that I have this done and it's clear to me how it is that I need to approach the problem, then I can write a formal proof. So let me now give you my first version, maybe of the proof, and then and I'll show you that okay, you can maybe improve from there, or that's maybe good enough. Let's see. Okay, so here's a proof. Proceeding by induction, we verify that when n is equal to 5, then 2 power 5 is equal to 32, which is clearly bigger than 5 squared, which is 25. So thus the basis of induction holds. Next, to establish the inductive step, let us assume that 2 power k is bigger than k squared. Okay, but now I look at my work. I already know where the obstructions are, so I can right away say that since k is for let's assume that this is true for some natural number k, where k is greater or equal to 5. Observe that since k is greater than 5, k minus 1 is greater than greater or equal to 4, and k minus 1 square is greater or equal to 16. As such, k minus 1 square minus 2 is greater or equal to 14, which is a positive number. Okay, all right. Next, if we then look at 2 power k plus 1, that's equal to 2 times 2 power k, which is greater than 2 times k squared, and this is true by the inductive hypothesis. which is then equal to k squared plus k squared. Okay, 2k squared. I don't need that. Now, next, 2k plus 1 minus 2k plus 1 minus k plus 1 square will then be bigger than 2k square minus k plus 1 square, which is equal to 2k square minus k square minus 2k minus 1, which is equal to k square minus 2k minus 1, which is equal to k square minus 2k plus 1 minus 1 minus 1, which is equal to k minus 1 square minus 2, which is greater or equal to 14, which is positive. So then we'll have that in summary, under the assumption that 2k is bigger than k squared for some natural number k bigger than 5, we have proved that 2k plus 1 minus k plus 1 square is bigger than 0, and this implies that 2k plus 1 is bigger than k plus 1 square. And that's the inductive conclusion. So therefore, by the principle of mathematical induction, we have proved, it's now safe to assert, it is now safe to assert that 2 power n is bigger than n squared for every natural number n where n is greater or equal to 5. All right. Another example for us to practice is the following. We want to prove that 1 over 3 4 plus 1 over 4 times 5 plus dot 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 plus 1 over n plus 2 times n plus 3 is equal to n over 3n plus 9 for every natural number n. All right, so for the basis of induction, we verify that when n is equal to 1. Then so on the bottom here we just have n, so 3 and then 4. Then 1 over 3 times 4 would be 1 over 12, which is clearly 1 over 3 plus 9. Okay, and so that verifies is the basis of induction. Next, for the inductive step, let us assume that 1 over 3 times 4 plus 1 over 4 times 5 plus plus 1 over n plus 2 times n plus 3. I want to use k instead, I'm sorry. Plus 1 over k plus 2 times k plus 3 is equal to k over 3k plus 9 for every natural number k where k is greater or equal to 1. Okay, now 1 over 3 times 4 plus 1 over 4 times 5 plus plus 1 over k plus 2 times k plus 3 plus 1 over k plus 3 times k plus 4 will be equal to, looking at the first k term, that will be equal to k over 3k plus 9 plus 1 over k plus 3 times k plus 4. And this is true by the inductive hypothesis. All right, and then if we factor, okay, so factor this out, we get 3 times k plus 3 k plus 1 over k plus 3 times k plus 4. That would be equal to 3, that will be equal to k plus 4 over 3 times k plus 3 times k plus 4 plus 1 over k plus 3 times k plus 4, and then we multiply this by 3. And this gives us precisely k times k plus 4 plus 3 over 3 times k plus 3 times k plus 4. As a scrap work, let me write down in red here where I'm aiming to. I'm aiming to get here k plus 1 over 3 times k plus 1 plus 9, which is k plus 1 over 3k plus 12, right? This is what I'm aiming for. So let me let's see if we expand everything out here. We'll get precisely on top, we'll get here k squared plus 4k plus 3 over 3 times k plus 3 times k plus 4. And then to factor this out, we look for factors of 3 that add up to 4, 1 and 3. So this will be equal to k plus 1 times k plus 3 over 3 times k plus 3 times k plus 4. And then notice that we can cancel these two things out, and we get k plus 1 over 3 times k plus 4, which is precisely k plus 1 over 3k plus 12. So we have this is we can see here, this is our inductive conclusion that we have derived. We started by assuming our inductive hypothesis, and then we derived inductive conclusion. So we can then finally say that by the principle of mathematical induction, I'm not going to rewrite the entire claim. Induction, the stated claim holds. The stated claim holds true. All right, so let's try to summarize how one approaches a proof by induction. If you're given a statement of this type, for every natural number n, p of n is true, then no, it could be, you know, n square 2n squared plus for every natural number n, 2n squared plus n is even, for example. Could be your p of n, right? So there are two steps. The first step is what we call the basis of induction. And for the basis of induction, there's only one thing that you need to prove. P of 1 is true. And then there's a second step, which is the inductive step. And the inductive step is usually the heart of the proof. It's usually the more challenging one. It's lengthier. It requires more work, and it requires proving an implication of the type P of k. If P of k holds, then P of k plus 1 holds. And for this part here, you often start by assuming that P of k holds, and then you connect this, which we call the inductive hypothesis, you'll connect this inductive hypothesis to the inductive conclusion, which will be of the type P of k plus 1 holds. And there'll be a therefore here. So this is the overall the overall structure of a proof by induction. Again, you verify the basis of induction by showing that the first is true. This one could be 5, 7, whatever, whichever is the first statement. And then you assume that P of k holds. Then you connect the inductive hypothesis to the inductive conclusion by using a direct proof. Thank you.